SMU-RFS.org, we are SMU-RFS, an innovative team of professional engineers who design solutions to the most complex problems of today. I am Alec Siems, high-level sprint director and electrical engineer.
I'm Skylar Shapiro, and I'm a computer scientist.
I'm Lanuza-Brown, and I'm an electrical engineer.
I'm Elise Lebiga, and I'm a mechanical engineer.
I'm Carmen Leung, and I'm an environmental engineer.
I'm Francesca Brogden, and I am a computer scientist.
In many third world countries, clean water, which is vital to life, is very hard to obtain. Getting to water in general is very hard in the first place because the water sources are in very secluded areas. And sometimes getting to these secluded areas means a trek through difficult obstacles, such as gravel, uneven terrain, local hazards, and even fire. Our goal is to make access to clean water more viable and abundant. We will do so by designing a robot that can autonomously navigate its way to the water, take a sample, and remediate it.
You came to us with an enormous problem. In order for us to solve this problem, we've broken up our solution into smaller components. This allows us to define how exactly our design solves the problem. We defined our solution as 4 interdependent blocks. First of all, we need a motor or some form of motion in order for the robot to get to the water. In order for it to get to the water, we need to program it to do so. Not only that, once our robot is at the water, it needs to be programmed to identify the turbidity, pH, and temperature. In order to get to the water, it also needs to have a proper structure and have the proper sensors attached to the robot. And in order to get that structure there, we come full circle needing a motor in order to move the robot to get there. Each of these sections have specific requirements.
We'll start off with the structural design. We need it to stand upright, fit all the pieces, maintain its balance, fit on the playing field, and be durable. These are the derived requirements. To fit all the pieces, we need to fit the Arduino, motors, sensors, and crane in a compact and organized manner. It needs to maintain its balance. When it's going up an incline, we don't want it to tilt backwards, or when it's on the rough terrain, we don't want it to be shifting to the left or to the right. It needs to fit on the playing field. It can't be wider than 40 centimeters for the maze, and it can't be taller than 418 centimeters for the fire overpass. And it has to be durable. We don't want it to run into a wall and then pieces fall off. So everything must stay secure. I've found that most of these are necessary except for the fits on the playing field. For some of these, we might not just do that obstacle and then the robot can still function properly. Next, we'll do the programming. We need it to be compatible with the Arduino. It needs to successfully align with the sensors to have it do what we want it to do. It needs to be autonomous. It needs to be able to move on its own, and it has to recognize its environment. These are the derived requirements. It only has limited connections to the Arduino. We only have so many spots where we can connect the motors, the servos, and the sensors. It also only has a limited power supply to put into the Arduino. One of the examples for the sensors is when it gets to a water well, it needs to know that at that point it's time to remediate. For recognizing its environment, it needs to be able to read the different colors taped to the ground, follow its pattern, and get to the right obstacle. It also needs to be aware of its hazards. I've chosen aware of its hazards to be a desirable because although it would be nice not to run into a hazard, it only counts points off and doesn't affect the function of the robot. Another important group is motor in motion. Of course, it has to get some way to point A to point B because it's autonomous and we can't be steering it. It's only limited to 2 motors and 2 servos at a time, so it has limited capabilities. It has to be able to handle rough terrain and redirect itself when it's off track, so it doesn't come to a place and then get stuck and not know what to do. The derived requirements for the way to get to point A to point B, we need it to steer left and right somehow, and move forward and backwards. A derived requirement of rough terrain is that it has to have good traction. I've chosen to have most of these as essentials, except for move forwards and backwards, Instead of moving forward and backward, we could just have it steer and then make a full loop circle. Exceptional traction is a desirable, but effective traction is an essential. Water remediation and testing. One of the major requirements of the robot is to check the water's turbidity, pH, and temperature. To do this, we need an arm to dip for testing, a way to mix the neutralizer in with the water, and a way to store and deliver the neutralizing solution. One of the derived requirements for checking water is to derive algorithms for accurate measurement. For example, to find pH, we use a voltage meter. We dip the voltage meter into the water, and using Nernst's equation, we can calculate the pH of the water. For the arm to dip, a derived requirement is that it can move up and down to reach different heights. Each obstacle has a water well of different heights, so in order to reach that, we need some way to move. The derived requirements to store and deliver the neutralizer are pump and pour out, has to be refillable, and waterproof. Mixing the solution with the water will give us a more neutral concentration throughout, and therefore give us more accurate results. Now that we have a better idea of what we want our robot to do, we can develop the procedures for achieving its task.
To develop the procedures for achieving tasks, I used a requirements list in order to develop what was essentially high-level pseudocode, and then refine that pseudocode to describe the general behaviors of the robot and the stimuli that cause the behaviors to change. The robot's default behavior is to simply move forward while receiving input from all of its sensors. Once that input changes significantly enough to trigger a change in behavior, the robot will take appropriate steps in order to deal with that change in stimulus. For example, if the robot is getting too close to a local hazard, it will change direction in order to avoid the hazard. Once the robot has reached the barcode denoting the entrance to a well zone and has determined which well zone it has entered, it will conduct appropriate procedures in order to navigate the hazards within the zone and locate and remediate the water. For example, once the robot reaches the zone representing Fishtown, Liberia, it will navigate the maze using distance and pump sensors until it reaches the water, at which point it will test the quality of the water, output its results, and remediate the pH based on those results.
In order to achieve these tasks, certain devices are needed. Every motor, sensor, and piece of electrical equipment will be attached to the Arduino board as shown. We plan to use 2 DC motors for the treads and 1 servo motor for the crane arm. There will also be a stirring motor that will be wired to the Arduino board for power. There are 7 sensors total, yet only 6 slots for sensors on the Arduino board. After consulting a quickstall.org employee, we decided to include an extra slot for the 7th sensor. Sensors include 2 light sensors, 1 distance sensor, 1 bump sensor, 1 turbidity sensor, 1 pH sensor, and 1 temperature sensor. The Arduino and all equipment will be mounted on the robot design shown in the next segment.
As you can see in the final design of our robot, there are many components present that will help us achieve our goal. We have decided to take advantage of a crane system for sensors and remediation and treads for motion. The crane gives the robot a long reach and requires few moving parts. It also has the ability to run on a servo, which eliminates the need for another DC motor, which would weigh down the robot. With the angled arm of the crane and the placement of the sensors on the end of the crane, the robot is able to reach over barriers and hazards near the water while adjusting to varying water locations. Using treads in our final design allows us additional advantages. Treads allow the robot to traverse various hazardous terrains that it may encounter in the field. The use of treads also allows the robot to be more compact due to the increased freedom in motor placement.
The placement of the sensors in our design is essential for our robot to achieve its task. We have placed 4 sensors on and around the front bumper to help the robot orient itself and identify water or hazards. The robot takes advantage of sonar to determine the distance, a bump sensor for collisions, and 2 light sensors for location identification and added safety. The 2 light sensors will be placed on the front right and front left corners of the robot. This allows the robot to not only identify its location, but also lets the robot know when it is near the edge of a ramp or wall. We place the sonar on the front center of the robot to allow it to see objects in front of the robot before a collision and determine its distance from objects. Below the sonar, the bump sensor will sense when the robot hits objects in the front of the robot. On the crane, we have also attached sensors to measure turbidity, pH, and temperature, along with a pump for remediation solution and a fan to stir said solution.
One alternative to treads is wheels. One of the largest issues with using wheels is the placement of motors. While we could get creative with gears to minimize the width of placing motors back to back, that would require more moving parts, potentially lowering the sustainability of the robot in the long run. Wheels may allow better mobility, but the size and lower traction outweighs the advantage.
An alternate approach to the crane would be a cherry picker system. This approach would take up less space but requires many more parts along with another heavy DC motor. On top of that, it also requires the robot to be dangerously close to the water source to test. This method also makes it near impossible to test water at ground level or below the robot.
In the next few weeks, we will begin physically constructing the robot. As the project progresses, we will continue to develop and improve the robot's design. Thank you. This has been a presentation by SMU-RFS.